Welcome, everyone. This is the second part of a three-part lecture series on Rydberg receivers. The Rydberg receivers are part of a larger lecture series on quantum sensors overall. So we're calling this the Quantum for National Security Committee lecture series. Today we're going to be hearing from Dr. Chris Holloway of the National Institute of Standards and Technology in Boulder, Colorado. The entire lecture series is on the screen right now. We're trying in this lecture series to bring nationwide experts in four most prevalent types of quantum sensors to try to give a common understanding to the entire Quantum for National Security Committee. We have a lot of different members, from highly technical individuals working on sensor development on through to business development people and diplomats working on export restrictions and the rules around how quantum sensors should be talked about between countries. So we're trying to give everybody a common level of understanding for what the different sensors are. That's the first lecture in each category. The second lecture in the category is meant to be about the applications that are most commonly discussed and why those things will be interesting to the future of national security. And then the third lecture, if it exists on the list, is going to be from a government individual trying to speak more to the government interest in each one of these sensor areas. You'll notice that some of these talks have an asterisk next to them. Those are open to the public, and the lectures will be recorded and posted publicly afterwards. Those without an asterisk next to them are only open to members of the Quantum for National Security TAC. So if you'd like to be a member, we certainly would like to have you. So Quantum for Economic Development Consortium is a group of government, industry, and academic stakeholders. It was launched by the Quantum Initiative Act in 2018 and currently has membership across 39 countries. This is the primary industry advocacy group in the quantum space. So if you're interested, there's a link for where you should go to try to establish membership for your organization. With that being said, today, we're going to hear from Dr. Chris Holloway. Dr. Holloway is the RF Fields Group Leader at the National Institute of Standards and Technology, has his PhD from the University of Colorado in 1992, and is also currently on the graduate faculty at Colorado as well. The silver and bronze medals from the Department of Commerce, and I feel like there might be more to say, but the bio I have from Chris is a little bit outdated. But in any case, what I do know about Chris is that he and his team were one of the very first developers of the Rydberg RF receiver space. They made their first demonstration in the early 2010s and have been leading this field ever since. And so you really are you're hearing from someone who's at the cutting edge of Rydberg receiver development, and I can think of no one better to tell you about what the applications are, because Chris is both a Rydberg receiver physicist, but also, as you can see from his work as an editor for the IEEE, very much just an RF expert overall. And so with that, I'm going to hand it over to Chris and ask that you please give him your attention, and we will have a 15-minute Q&A session at the end. So please, as you're listening, think about what you'd like to ask, and we will talk to him after the fact. So with that, I will hand it over to you, Chris.
Well, thank you. First of all, let me say, can everyone see my presentation mode now?
I can see it.
Very good, thanks. First of all, Eric, thanks for the intro, and I hope I live up to some of your expectations here, but I'll give it a go, and we'll see what happens. What I want to do is sort of talk a little bit about the development of these Rydberg sensors, maybe talk about where we were, what we've done, us and various other groups, and then where some of it might be going in the near future. This is a project that I started probably about 2008, 2009. And the real purpose was to come up with an absolute direct traceable measurement of electric field, which we really didn't have before. We could do an SI traceable measurement, but it was very convoluted to get there. So we wanted to come up with a better way of doing that. And we knew if we could, the atom responds very well to an environment you put it in. If you could do a measurement based on some atomic transition, we could get a better measurement for an electric field. Well, that sounds good. It turns out this field has sort of exploded in probably the past 5 years. I could probably give you 15 to 20 companies who are either started programs or in the process of starting programs in these Rydberg sensors, receivers, caveat. And so what I want to do here today is try to summarize the development, talk about a bunch of applications, and then get into some commercialization efforts that various groups are doing, including I'll just talk briefly about a new DARPA program, just give a highlight of what they're trying to do in this area of commercialization. With that, I just want to say that from a calibration viewpoint, I work at NIST. Our mission here is to do the best traceable measurements that one can do. But it turns out that probably 99.99999% of the world could care less that you could do a traceable measurement of electric field. So, why are so many people interested in this technology? So as a motivation, I want to start with a video here. And I hope this works. Let's see. There we go. So I'm going to pause this just a second. If you see, this is my group. We're in the lab playing a video game. And if you were a bean counter or a manager, you might be concerned that we are in a lab playing a video game. And you see we're playing it real time, zero latency. It's we're just playing this video game in real time in the lab. And it's not that we're playing the video game, it's actually how we're playing the video game. And this is what has gotten a lot of people excited about this technology. And hopefully you can see my phone, my camera here. What I'm holding up is a vapor cell. This is a glass cell that we've got either rubidium or cesium atoms in it. And basically how we're playing this video game is we're taking a game cube, taking the output of the game cube, AM modulating a carrier and shining that modulating signal onto this vapor cell. And basically we shine a laser through the vapor cell, the laser goes through the vapor cell, hits a photodetector. We take the output of the photodetector and put it right onto the CRT. So this modulated signal is basically modulating the atomic states of these atoms, of these Rydberg atoms that we have in here. And we can detect that modulation directly on a photodetector. The idea being that there's no antenna receiving this signal. The atoms are acting like the antenna. And if you look, there's no down-converting demodulation electronics whatsoever. The only electronics we have, putting the lasers aside, is that we have a photodetector that's going to a CRT. So here we're replacing antennas and all this front-end electronics. So this is what's gotten people interested in this. One nice thing about working in a lab is we do all kind of cool science. And usually when you do cool science, when you start to write a paper, there's usually some discussion who gets to be first author on a paper. When we published this paper a couple of years ago, it was pretty easily decide who was the first author. We all played the video game, and one with the high score got to be the first author here. It turned out to be, at the time, a postdoc. Now he's staff here at NIST, Nick, who apparently spent way too much time as a youth playing his video games. But anyway, that's what has gotten people interested in this. So before I get going on the whole aspect of developing of these Rydberg sensors, I want to give a little bit of a perspective of why NIST got interested in this. And hopefully most of you guys know who NIST is, but we're a federal lab. Our mission in life is to promote U.S. industry through, advancing measurement science, standards, technology, and basically just to enhance economic and security improvements for quality of life. That's our mission statement. Basically, we have two campuses. We have a campus in Gaithersburg with about 3,500 researchers. And then in Boulder, we have a campus where I'm located. We have anywhere from 700 to 800 researchers. These numbers vary because we have several postdocs and visiting scientists that work at the labs. Our basic mission in life is to do weights and measures, but we also look at fundamental research to look at technologies that might come up 5 to 20 years down the road. And this is sort of an example of that. This is a project we started about 15 years ago, thinking about it. And we're starting to see maybe 5 years out. I know there's a company or two out there that actually have products that they're starting to sell, that you could go online and look for. And then the idea of coming up with really true receivers for particular applications may just be a few years away. So that's what we're trying to do with this project. Get us to a point where you actually might have some products coming out of this. So the question is, why do we need standards? Why do we need these? A good example of why standards are needed is that when NIST first got started, I think it was formed in 1901, 1902. If one traveled around the country, I heard that there was anywhere between 40 to 50 different volumes that people were calling a gallon. So there was no standardization. So you needed standards for commerce. And that's one reason why NIST is in the Department of Commerce, is because we're trying to innovate commerce here through standards and so forth. How does one, correlate standards and make sure we're all doing the same type of measurements? It's all done by all of us doing measurements traceable to some international system and units. And then in our case, the SI, and it's the National Bureau of Weights and Measures that sort of coordinate all these national metrology labs around the world to make sure we're all sort of doing the same type of measurement. I'd like to give a little interesting anecdote here, and that is, why are pirates responsible for the U.S. not being on the metric system? My understanding is right after Thomas Jefferson, right after the Revolutionary War, Thomas Jefferson felt that the U.S. should go to the French system. So he lobbied quasi-Congress at the time and got a chunk of money. He sent that money to France, and France, put a bunch of artifacts together, probably a meter stick, maybe a kilogram ball, maybe even a liter, some liter for volume, put it all on a boat, shipped it over here to the U.S. Off the coast of the U.S., off the East Coast, pirates took over the ship. And I'm assuming they opened up the chest, saw all these meter sticks, all these metric units, these artifacts, and they basically threw them all overboard. And so as a result, Thomas Jefferson had no more money to buy any more artifacts. And so the U.S. is unfortunately stuck in the Queen system right now. But with that said, what is an artifact? An artifact is something that we would use to transfer information. And that being a meter stick, we have a mass, a kilogram, and then what I've got shown here is the official half bushel that the U.S. used to use in 1857 for measuring grains and so forth. In fact, if you go to the NIST library/museum on the NIST campus in Gaithersburg, you can see this official half bushel here. Artifacts sound great, sounds like a good idea, but they change. So we need a way of coming up with a better way of doing a traceable type of measurement. And the last artifact that we had was the kilogram. And the kilogram ball, basically we got rid of that in 2018. And now all our measurements that we do now are traceable to fundamental constants. And what's important to us here today is the idea of Planck's constant is now a fundamental constant defined by the SI. And with this Planck's constant, we can now make measurements of things like electric field and power traceable right to Planck's constant. So that's what we'd like to do. Another reason why I like to, talk about the importance of standards is this is an excellent illustration. Back in 2 BC, that's 2 years before COVID, I was at a meeting in Las Vegas, and I took this photograph here. World's largest pint. I would argue that's like saying NIST has the longest second, or we have the world's longest meter stick, right? A second's a second and a pint's a pint. And from our side of things, what about electric field? How do we measure an electric field? The problem before we got into these Rydberg sensors is that we had this chicken and egg problem, that if you wanted to have a probe that you could make a measurement of an electric field, you would have to calibrate that probe. And to calibrate that probe, you'd have to put it into a known field. But to have a known field, one had to have a calibrated probe. So you had this chicken and egg dilemma. And there's ways that NIST and other national metrology labs and institutes around the world generate what we think is a known field based on Maxwell's equations and so forth. We use things like anechoic chambers or TEM cells that we can generate what we think a known field is. We have an antenna. We know some property of this antenna. Maybe we've calibrated its gain. We know power going into the horn antenna. We go some distance X away. We put a probe or some sensor head that we're trying to measure there. With Maxwell's equations and the distance, separation, and so forth, we can calculate what we think the field is. On a really, really good day, when all the crystals are aligned around our chambers here in Boulder, we think that we can do a measurement. We know the field to about 5%. It turns out, in reality, industry would state this, and on a typical day, we don't know the field better than 10%. So we would like to do better than that, and can we? And we can do that by going to the atom. Because we know the atom responds very well to the environment that we put it in. And so if we can figure out how to read out how this atom is responding, in our case to an electric field, we can get a good sensor. And how we do this, we generate Rydberg atoms, and then we use a technique called electromagnetic induced transparency. It's the most common way that we'd read out the response of the atom, and from that we can get a traceable measurement. And the idea is that, and we probably you guys heard this from Gallagher's talk, basically a Rydberg atom is an atom where we take one of its outer electrons and we excite it to a very high energy state. Basically, we move this electron very far away from the nuclei. And when you do that, you have this very large dipole moment. And so you have these huge dipole moments that can be generated in these Rydberg atoms. And therefore, they're very sensitive to electric fields, and they make very good electric field sensors. The most common way of reading out how this atom is responding to this electric field is by a technique called electromagnetic induced transparency, which I'll talk briefly about. And here you can look at on-resonant techniques of looking at ultrasound splitting, or you can look at off-resonant techniques through Stark shifting and so forth. This is the most common readout form. As we'll see a little bit later, there's other types of readout forms that both us and some other groups are looking at. That includes fluorescence, that includes things like 6-wave, 4-wave mixing approaches that maybe give us some advantages for more sensitive measurements, but we'll talk about that in a minute. The basic idea that we're trying to do in these Rydberg sensors is take your conventional antenna or receiver that basically relies on conducting currents flowing on some metal geometry, and we're going to replace that with a glass cell full of either rubidium or cesium atoms. We interrogate the atoms with some laser, some probe beam. We look at the response of the atom, and we can get information about the time varying field hitting the atoms. And we'll see that allows us to do things like receiving AM, FM, phase modulated signals, angle of arrival, and a whole slew of other applications. A little bit of historical perspective here, just to give us an idea of what's going on. I say 8 years, I guess it's maybe even 15 years now. Prior to 2010, people knew that Rydberg atoms were highly reactive with electric fields. Gallagher and others have demonstrated this for many years. Around 2010, we wrote a paper talking about, with this new definition of the SI coming down the road and Planck's constant, we could actually get an SI traceable measurement for a field. It took a while to get some leverage here to get this project going, but about 2010, 2011, DARPA started funding a couple of groups to look at this. One was led with the University of Oklahoma with Jim Schaefer and some people at Stuttgart to start looking at this. And then they also, there's a group here at NIST and working with some guys at the University of Michigan, Georg and David, in their lab. We started working in this field, started making quite a bit of progress since 2014. And I would say because of a lot of this progress, a lot of it from these first two groups, but now there's a lot of groups out there really spending a lot of effort looking at this. And it's because of this, there's several groups now around the world, including national metrology labs, private industry, universities, other government labs that are starting programs in this area. And I just have a few mentioned here of companies, countries, government labs, national, international, universities. And I have a list of, 5 or 6 U.S. companies here. I know of probably 10 or 12 others that I know have started programs in these Rydberg sensors that I can't really mention their names. But the idea being that this is a pretty rapidly growing field, especially in the past 5 years. Now, as I said, the most common way to read out how the atom's responding to this electric field is electromagnetic induced transparency. And I'm sure some of you have seen this before, but just a really brief illustration of what we're talking about. We have a vapor cell. It's got rubidium or cesium in it, basically a cell like I've got shown here. We basically shine a probe laser through here to monitor the response of the atom, basically look at its energy state. We have a photodetector, and we can represent this sort of simplistic picture as a 4-level atomic system. And basically, if we scan the laser across this first ground state transition, you get your standard inverted bell curve. Basically, this is spectroscopy. It's atomic spectroscopy experiment. And we get our inverted bell curve here. If we turn on a second laser here, in this case, this 2 to 3 level transition here, you get this quantum interference, you get some coherence that gets developed. And what happens is normally where you would have absorption, you get this very narrow window, we get a strong transmission signal that comes through. This is a EIT, electromagnetic induced transparency. The idea is that we had a light, the 780 light was basically being absorbed until we turned on the second laser, and then it gets transmitted through the environment, through the vapor cell. And people have known about this for a number of years. People have done slow light experiments with it. You can stabilize lasers with this. In fact, some of our laser stabilization techniques we use in the lab is using an EIT stabilization. And so people have known about this for years. The trick here is that if we choose the second laser such that we drive this atom up to a Rydberg state, so we're at a very high energy state, the next transition we can be coupled with an RF photon. And if we turn on this RF photon, we basically perturb the energy state here. And what happens here is this EIT line basically splits into two. And with a little bit of effort, one can show that the splitting is directly related to the amplitude of the applied field. If you invert that, it basically says that if you can measure this splitting, which is on the order of megahertz, we can then get a measurement of the applied incident field. The key here is frequency is something we can measure very accurately. Planck's constant is now an SI-defined constant, and our only quasi-unknown is the dipole moment of the atom, but we can argue that we think we can calculate this better than 0.1%. So therefore, we've basically taken an amplitude measurement, an amplitude of an RF field, and reduced it by basically just measuring an optical frequency. And the traceability comes from the fact that we get a direct measurement of electric field traced right back to Planck's constant. In some sense, it seems complicated, but from an atomic physics viewpoint, this is probably one of the easier experiments one can do. All it requires is a vapor cell, some probe laser, in our case, 780 here for rubidium. We have a photodetector. We have our coupling laser, 480 for rubidium, and we have some source. Some here in this case is a horn antenna. We vary the power hitting this horn antenna. We vary the fields at this vapor cell, and we can detect that. Take the photodetector, put it onto a scope, and this is what one would see in a typical experiment. Power feeding a horn antenna, shining on this vapor cell. We shine lasers through the vapor cell, look at the output of the photodetector on a scope, and this is basically what you see. That as you start increasing the power in this horn antenna, this EIT line starts splitting and separating. And the experiment basically is measuring the separation between these two peaks. Planck's constant dipole moment, we can tell you what the field exposing the atoms to. And just real simple, once again, this is a case of an EIT line with and without an applied field. This is for a cesium atom experiment we did. But it gives you an idea of what you can actually see on the scope. So our first sort of proof of concept experiments on this were happening about 2012, 2014. And this curve sort of illustrates a lot of interesting things here. What we did in this, to collect this data, we basically took a horn antenna, we drove it with a SIGGEN, varied the power in a SIGGEN, and we looked at the field at this vapor cell. So this power in the SIGGEN, this is the electric field at the vapor cell. The solid and dash curves are what you would get from a Maxwell's equation type calculation. The circles are what we get from the EIT approach. By measuring the splitting, Planck's constant dipole moment, we can get the electric field. And you see here, first of all, there's very good correlation. But more importantly, what this figure shows us is this was all done in the same setup. The same vapor cell configuration here, we were able to measure fields from, in this case here, 9 gigahertz up to 132, actually 182 gigahertz. The idea is, this is initially what got people excited about these vapors, about this technique, is that with one small quasi-compact vapor cell, and we're going to see examples where we got vapor cells down to 2 millimeter thick and some that are 10 by 10 by 10 millimeter cube cells. So with these one compact vapor cell, we can measure fields from basically very low frequency to very high frequency. Initially, I used to say that we can measure fields from 10 megahertz up to a terahertz. Just recently, we've been demonstrating field measurements down to 20 kilohertz to 1 terahertz. So the idea of having one compact vapor cell or vapor head or sensor head that allowed you to measure fields over this huge dynamic range of frequency has gotten a lot of people interested, especially from the low frequency side. The idea that now you truly have an electrically small antenna, if you want to think of it that way. The atoms, the size of the vapor cell is much, much smaller than the wavelength of the frequency you're trying to detect. And for those of you who do RF measurements, you might realize that at low frequencies, to get an efficient receiver, you need a very, very large antenna. So that's what initially got people interested in this. From a NIST perspective, our interest is above 110 gigahertz. Currently, there's not very good techniques used to calibrate instruments above 110 gigahertz. And we think this is going to be a path forward to actually do that. So here's a very interesting curve that is for everyone to leave this talk with. I data mined about probably 100 to 150 papers that were published since 2010. And what I did is I wanted to look at what frequency range and first what minimal detectable fields people were claiming they could detect. And so I just did a scatter plot here. You see rubidium and cesium is typically what we're using. And what it shows here is that around this, 10 to 20, 30 gigahertz range, maybe down to 5 gigahertz is an optimal sweet spot people like to work in. Slowly, we're seeing people moving down to lower frequencies. These are newer papers over here, and there's even some newer papers where data points are going to be over here somewhere. And then people are moving to higher frequencies. So it gives us an idea what people have been doing with these in the past 10 years. Maybe equally important is sensitivity. Sensitivity, this is a plot, and I've got it years versus sensitivity. And, this is Schaefer's paper in 2012, 2014. It turns out it looks like there's a lot of missing data here. It turns out there's not a lot of missing data. A lot of this data here is in this time period. The only thing is a lot of these papers here only give minimal detectable field. They don't tell you how long they average to get that minimal detectable field. So with that, I could not put the data onto a sensitivity curve. But it still gives us an idea that while data is missing here, there was still quite a bit of work being done in this time period. But then as time moved on, we started going to optical homodyne. And then about 2018, 19, when we introduced a Rydberg mixer, now people are going to RF heterodyne techniques. And you see the sensitivity being driven down as the years go by. This one data point here is actually based, and we'll talk a little bit about that. This one data point I have right here is not on conventional EIT type of sensing. This is actually based on 6-wave mixing. So 6-wave mixing, they're really driving the sensitivity down. But anyway, just some data to keep in mind. So it turns out if you could actually do amplitude modulation, which is all we could do up until about 2018, one could do, amplitude detection. One could do AM and FM type modulations very easily. And the idea being is as you recall, when we turned on a CW carrier, we basically, these peak splits into two, and we get these two ultrasound peaks here. If you were to have AM modulation or FM, where you're basically monitoring the modulation of that carrier, one of those peaks just wobbles back and forth. So if you can lock your laser to one of the sides of one of these peaks, then the output of the photodetector is just a baseband signal. And numerous people have demonstrated that for a number of years, had demonstrated that, starting to about 2018, I think. Several groups have looked at how you would actually do AM, FM type modulation. I always find that sometimes you can look at data all you want, but if you hear something, it's a nice way to sort of get a more visualization of what's going on. This is a demonstration we did just to do a cute little trick where we basically took an acoustic guitar. I brought my acoustic guitar into the lab. It had a electronic pickup. I took that the electronic pickup and I used it to AM modulate a 20 gigahertz carrier. I shined that 20 gigahertz carrier onto this vapor cell, put a probe laser through the vapor cell, took the output of the photodetector and set it into a set of speakers or into a computer, and I could play the guitar, and this is basically the baseband signal coming out of the photodetector. If I take that photodetector and just hook it into a set of speakers, this is what you hear. So I don't want you to lose sight of how simplistic this actually is, right? That I'm basically AM modulating a carrier, shining this AM modulated carrier onto the vapor cell. The atoms in the vapor cell act like the antenna and do all the down converting and demodulation for you automatically. And what you're hearing is just the output of the photodetector. So you see it's very dynamic. You hear a lot of highs, lower lows. It's got a lot of dynamic range. So as I said, that's what initially got a lot of people very excited about these types of receivers. In some sense, forgetting the lasers aside, it's a very simplistic system. And so once again, the advantage here is the atoms are automatically doing the receiving, acting as the antenna, and doing the down diverting, the demodulation for you. Another advantage of these types of systems is, if you think about it, the atom is a highly resonant structure. So it has a lot of potential of doing broadband, multi-band receivers. And there's a whole range of techniques that are just starting to come out. I know of a couple of papers coming out here very soon that looks at receiving multiple band signals simultaneously in one vapor cell. And just to initially demonstrate that, what we did basically is put cesium and rubidium in the same vapor cell. We took a piece of music that had an instrumental part, piece of music that had a vocal part, split those apart, AM modulated two separate carriers, shined it onto the vapor cell. And basically what I'm showing here is the output of the photodetector, original instrumental, original vocal, received instrumental, received vocal. These are received simultaneously with two separate speakers. Actually, you're hearing this in stereo. And if I can get this playing, what you can hear here, I think, give me a second. Come on. There. So once again, this is two pieces of data being sent simultaneously over these two cells, these two atomic species, one cesium and rubidium, and we're able to pick up basically in stereo here. Once again, just to show the simplicity of these types of receivers. No electronics, no front-end electronics, and stuff like that. We're slowly trying to understand bandwidth issues of these. What are the initial bandwidths that we can receive and how can we might improve that? Right now, we can pretty easily do about 5 to 8 megahertz pretty easily in the lab. And to demonstrate that, what I have here is we basically took a webcam, the output of the webcam, AM modulated a carrier, shined it on to a photodetector. And basically what you're going to see here is the yellow curve is the output of the webcam. The blue curve, or excuse me, the pink curve is the output of the photodetector. We then take the output of the photodetector and we put it into the CRT. And basically what you're seeing is in the lab in real time streaming video. So here's our webcam. There's us in the lab. We basically take that output AM modulated carrier, shine it over the atoms, and we can receive video, color video, pretty sharp color video without any down converting electronics or an antenna. The receivers are doing that automatically for us. So a really nice application. We know for this particular scheme that we're using that this video scheme, it requires about 4 megahertz of bandwidth to get color. So we know we're picking that up pretty easily here. We talked about playing the video game, the same idea, AM modulated carrier with the GameCube. We can show the video game. And, I won't show the video again, but the key point here is that we're slowly starting to understand how we can manipulate the receiver to get either bandwidth or sensitivity. And this is the case where by manipulating the receiver, we can play the video game in very fuzzy black and white, very low bandwidth. Slowly increase the bandwidth so we can get sharp color or sharp black and white, increase the bandwidth more, and we can get sharp color by playing the game. A little bit more on a historical perspective here. Most of the work up until about 2018 was all based on trying to understand how to measure the magnitude of the field. There was some work looking at polarization. And if you do magnitude, you could do AM and FM type receiving. It turns out the missing link was phase. And about 2019, we introduced a technique of measuring phase. Now we can actually fully characterize the phase, amplitude, and polarization of a time varying signal all in some compact vapor cell. And that's starting to open up a whole range of other applications. From the how we actually measure phase is we generate something called a Rydberg atom mixer. And the basic idea here is that we have a signal we're trying to detect. We have an LO that we shine onto the atoms. These two signals create a beat note, and the atoms automatically pick up that beat note right on the photodetector. And basically, this is the output of the one of the beat notes for different phase conditions here. And by monitoring the beat note, we can actually get phase of this signal. And just a real quick, dirty illustration of that, we basically took a electronic phase shifter, put it in line between a SIGGEN and an antenna, shine it onto the vapor cell, vary the phase of this phase shifter, and then compared that measurement to what you would get from a VNA of the phase shifter. And this is basically the beat note right off the scope. So you see very clean beat note signals here, and relative phase of that beat note is the phase of this phase shifter. And this is just correlation between what you'd get from a VNA, vector network analyzer, and the atom-based measurement. So you see very good correlation here. One can do little tricks like try to measure the propagation constant of free space. One can do that if you can look at the phase. The propagation constant is basically the change in phase as a function of distance of some incoming plane wave. And basically, by putting the antenna on a translation stage, measuring the change in phase as a function of distance, we can get this curve here. The slope of this curve is propagation constant. And sure enough, you show that the mixer gives us 409.3. The analytic calculation says it should be 409.7. So we do a very good job of measuring phase. So we can do that. What can we do with it? The real selling point is, can we truly measure a phase modulated communication signal, similar to maybe the modulations being done in your cell phone? And I would say, yes, we can. This is a demonstration where basically we took a 247 random bit stream, shine it over the atoms. We used QPSK, PPSK, and QAM. Basically, this is changing the various phase states of this communication signal. And if you look at this, it's pretty impressive that we could actually measure 64 QAM. That's 64 simultaneous phase and amplitude states that we can measure with these receivers. Once again, the big advantage here is we can eliminate some of the front-end electronics. This is just an example too of how we can make these things sensitive enough that we can basically set a cell phone up here, hook up some link with the cell phone, and we can actually detect what's going on in the cell phone. Detect the signals pretty readily. Well, with this mixer, you can do other things. And the other things you could do with a mixer is that you can improve sensitivity. In 2019, we demonstrated this where if you basically took an LO, shined it onto the vapor cell, you have some incoming field. In some sense, this LO is helping to amplify or enhance this incoming field. And so the amplitude of the beat note is relative to the amplitude of this incoming field. And this helps amplify a weak signal. When initially did this, I think we were able to detect with the 46 microvolts per meter. About a year later, it was improved on by a group in China. They were down to 5.5 microvolts per meter. And then we improved on that a little bit more by using some things like optical repumping, and we're down to 3 microvolts per meter. I know I've heard reports of people are lower than this, but I just haven't seen it in the literature yet. And I might mention, this is a common approach now people use to do sensitivity. There's some newer approach that we'll talk about in a minute that are coming out that maybe eliminate some of this. But this is the common approach people use to try to improve the sensitivity of these particular receivers. So keep in mind that, now that we can measure amplitude, phase, and polarization, that opens up all this idea of doing receivers. But that also opens up a whole range of other applications that people are interested in. One of the applications is angle of arrival. This is a case where we basically took a vapor cell. In this case, we just used two different locations in the vapor cell. We put laser beams through two different locations in the vapor cell. We can determine the phase of some incoming signal at these two different locations. And the change in phase, or the relative phase between these points, tells us something about the angle of arrival. So now we can start thinking about making phased arrays where we can now look at angle of arrival and other imaging applications by measuring basically the amplitude and phase of the field. And this is just a plot of us demonstrating angle of arrival. We basically took a horn antenna, rotated around the vapor cell, measured the relative phase, got angle of arrival from the atoms, and basically what you'd get from a theoretical calculation. So very good correlation of angle of arrival here. From a NIST perspective, we're also looking at other applications here. One is coming up with a voltage standard. The idea being that this is not going to compete with your standard Josephson junction where you have incredible uncertainty on voltage. The idea, though, this can be a very easily and maybe inexpensive transferable standard for voltage. The idea here is that we apply some voltage across these parallel plates. We put lasers through these parallel plates here in between the plates. We measure basically a Stark shift of the energy state as we increase the voltage. That Stark shift gives us electric field. Knowing the separation between the plates, we can tell you what voltage we applied across the field. So we're looking at these alternative for some type of SI measurement. Another type of measurement we're trying to look at is power. A conventional way people do power measurements now. There's also some unwafer techniques, but typically it's done in a waveguide. You've got some waveguide. We know Maxwell's equations tell us the fundamental mode in a waveguide takes on some side wave distribution. If you can estimate the peak value in this waveguide, one could get at the power. So if we can use Rydberg atoms to measure this electric field, and we know some uncertainties on the waveguide dimensions and some constants here, we can get power. And this is our first set of measurements where we took a waveguide, filled it full of atomic vapor, shined lasers through here, measured the electric field in the waveguide, and we can get power. One of the key advantages of doing this sort of new way of doing power is that it allows us to do, we'll call it real-time in situ measurements. People would like to have sources that you could have calibrations built right into the source. So using these Rydberg atoms allow us to actually build power meters right into a source so you know what power you're actually using during your application or your experiment. Moving on, other applications that we're trying to develop here at NIST is if everyone looks on your cell phone, you have a very nice camera. Wouldn't it be great to have an RF camera so you could take a snapshot of some RF field? Well, we're trying to develop such a device. We're trying to build we'll call it an imaging array, a beam profile, whatever you want to call it. But basically, this is our first prototype here. It's a 10 by 10 element array that allows us to take a snapshot in a two-dimensional plane of magnitude and phase of a 26 gigahertz carrier. And so once again, we're trying to look at other applications of imaging applications of these sensors. Most of the drive lately in the Rydberg atom sensor world is sensitivity and bandwidth. And the sensitivity, people are looking at different approaches to get there. I'll call it an atomic physics approach, and then there's electromagnetic approach. The atomic physics approach includes optical pumping, 3-photon, fluorescence, and 6-wave mixing. And the electromagnetic approach is basically trying to take these vapor cells and embed them in cavities or resonators. The optical repump approach is actually quite simple. Instead, we basically take our 2-photon scheme of getting to a Rydberg state, but we just add a repump laser here to take some of the atoms out of this other ground state and pumping into another ground state that we can interact with. And one can show this very simple measurement can increase your sensitivity by almost a factor of 2 or more. And this is what allows us to get down to 3 microvolts per meters per root hertz. The other approach that several groups are looking at is the idea of using 3 photons versus 2 photon excitation to the Rydberg state. The issue of the 2 photon is that because we have 2 different optical beams that have a wavelength mismatch, we have an inherent broadening of our EIT line. And this broadening can be on the order of, say, 5 to 6 megahertz wide. So obviously that's going to affect, if you're looking at ultrasound splitting, if you have a very broad peak, that's going to affect how much splitting, the luminal splitting that one can detect. So if you can reduce this line width of this EIT signal, you can in principle improve your sensitivity. One way of doing that is using 3 photons to get to the Rydberg state. And you choose optical photons that gives you the best mismatch of your Doppler. And as a result, you can get very, very narrow lines. And in fact, I think Schaefer produced a paper, I think, where he's down to, I think he said, 300 kilohertz that he's got his line widths down to. We're running 3 photon systems in our lab, and we're down to 300 kilohertz well line width. And so in principle, those narrow line widths, which order of magnitude better than what you do with 2 photon, in principle give you a better way of doing sensitivity. Another approach that we're looking at, and we know a couple other groups are looking at, is the idea of doing fluorescence. This is a paper that's just coming out, where basically we used 3 photons to get to a Rydberg state. We used an RF field to drive to some additional state, and then we basically measured fluorescence off that 510 decay. And these are just simple data sets here. But with just the initial setup we did, we're able to get down to 10 microvolts per meter per root hertz by just looking at fluorescence. Another exciting approach that a lot of people have gotten are interested in is based on the paper that came out from the group in Poland about probably earlier this year, and is based on a 6-way mixing approach. The idea basically is you use 2 photons to drive up to a Rydberg state. RF drives you up to an F state. Use a dressing laser to get to a D state, and then you get this generated photon here that you detect on. And with this approach, they were showing that they could get down to 0.39 microvolts per meter per root hertz. So there's a lot of attention of seeing where this new sort of a sensing approach, different than what you would do from a conventional EIT type scheme, of seeing what this might do for sensitivity. Then from the electromagnetic viewpoint, there's the idea of putting these vapor cells into cavities or resonators. This is an example of a very simple structure we built a couple of years ago. We have a vapor cell here, just took a split ring resonator, put it over this vapor cell, and this very simple design gave us an improvement in sensitivity by a factor of 100. So a very simple design, dramatically improvement in sensitivity. Obviously, the disadvantage here is this in principle is a narrowband system, but there's a paper that I think is coming out soon, where a group has demonstrated they now have a variable controlled split ring resonator, and they can get this type of sensitivity over a pretty broad bandwidth. So sort of interesting application space here. And then this gets into the area, I'll call it Rydberg engineering, that now we're starting to really understand these systems enough that we can start doing a lot of interesting things. And obviously people would like to be able to measure waveforms, and there's various groups have got various techniques out there now that you can almost start measuring these types of waveforms, say a chirp waveform if you want to measure it. And there's different schemes that people are using. There's schemes out there that people are able to show they can detect anywhere from 12 to 14 simultaneous frequencies at once. And with that, you can start developing waveform analysis from that. There's techniques where you can dress the atoms with either additional optical or an RF field to drive these Rydberg states or mix these Rydberg states together so that you could start doing continuous frequency tuning, continuous on-resonant frequency tuning. There's techniques out there where people are looking to go to low frequency and there's various schemes out there. One is using Stark DC, AC Stark tuning to go low frequencies. There's some techniques called Rabi flopping, using sidebands, Flow-K sidebands to look at low frequency. So there's a lot of push right now of driving these sensors to low frequency. And as I said, that in the lab we've demonstrated easily down to 100 kilohertz, and we've even done 20 kilohertz in the lab. And I understand some people are even going lower than that. But there's some caveats with those types of measurements. Everything I've talked about now has basically been based on, I'll call it warm or hot vapor. These are basically vapor cells at room temperature. From a NIST perspective, we're also looking at other sensors that may be based on cold atoms. In particular, we would like to have a black body detector for the purpose of maybe helping better characterize temperature or thermometry. And there's a whole reasons why we want to do this that I don't want to get into right now. But it's the idea that if we can drive these atoms, these cold atoms, up to some Rydberg state, then black body helps redistribute their populations into various nearby states. And if you can read out these various populations, either through ionization, fluorescence, or selective field ionization, if you can read out these various populations of these various states due to black body, you can get at temperature. And we got our first set of data about 2 weeks ago. I'd just like to show this. This is our mosh pit. This is basically our atomic cloud inside our chamber here. We think we have about 10 to the 6, 10 to the 7 atoms in here that we're moving around. With this, we're able to actually do an experiment. This is very initial results. We drove up to this Rydberg state of 32S. We then let black body redistribute the population. And with selective ionization, we can detect these populations. And this is a plot of relative population between these various states, first set of data. And I'm not going to tell you what that secret number is because we've got a paper coming out on this very soon, that we're able to now start measuring temperature with these types of Rydberg sensors. We hope to, with further averaging, to really drive a very fine resolution of temperature. But it's really the first set of measurements to show that we can actually now start measuring temperature with these Rydberg systems. So, as I said, over the years, they've been quite a bit of progress. NIST, Oklahoma, Schaefer's group, Michigan, and then we started seeing various other groups emerging, both in Europe and in Asia. And now, because of a lot of this progress, several groups now are starting to look at what the potential of these systems might do. Once again, they're not going to replace the cell phone as a receiver, but there's some niche applications where this is going to be a very interesting application space. And I tried to group some of these application spaces into some categories. I call it SI traceability. This is probably the NIST perspective that most people could care less about. The idea that we can now have an SI traceable electric field measurement, SI traceable power measurement, and SI traceable black body detection. There's receiver applications now, and we're talking about we can measure AM and FM type signals. We can measure phase modulation signals, QAM type signals, QPSK type signals. And the idea now we can start thinking about receivers that maybe could take advantage of these atomic systems that maybe is a different protocol than what a conventional receiver is doing. And that's where some of the really interesting aspects of research in the receiver world is going to. There's imaging space I talked about. I talked a little bit about an RF camera. There's near field imaging. There's subwavelength imaging people are looking at. And then there's this whole array of other applications that people are starting to look at that has made the field sort of really interesting. Obviously, to get this field to go someplace, we need to get off this optical bench, and we need to go to more compact form factors. This was our first attempt to do that. This is a 10 millimeter cubic cell that basically we fiber coupled to, and this allowed us to move this fiber coupled cell at least away from the lasers that were on the optical bench. And we did a whole series of measurements to show what you could do with these compact vapor cells. We want to start making these things smaller, and we're sort of going that way. There's various other groups out there that are doing the same thing of trying to look at, sorry, my phone. No, there we go. Sorry about that. Of trying to make these things smaller. And this is our attempt at making sort of a somewhat portable vapor cell portable system. This is a system that we took to Clio about a month ago, and demonstrated video and game playing with the vapor cell. Here's our lasers on top of our one board. We've since made this thing smaller, and our next generation is make this even smaller. And I'll talk about that in just a minute. The point of we're trying to do with this, we're looking at, and this is something that we've taken to a few places to demonstrate some capability. Right now I've got this system in our antenna chamber here, where we are basically, sorry about that. We are trying to look at different capabilities of trying to make some more direct comparisons between these atomic systems to conventional systems. And we're doing that in some calibrated chambers that we have. Well, from a technology development viewpoint, the things that we need here is very mass-produced miniature vapor cells. I mean, we would like to make thousands of these at a time. We want them all to work. And it turns out the Rydberg sensor vapor cells are much different than different requirements than what you would have from a magnetometry. People are mass producing magnetometry vapor cells already, but the Rydberg cells, compact cells, bring another can of worms to the problem that we're trying to work out. The other application space, it come up with a compact, high power visible lasers. That could be green or blue, or I should say just compact lasers in general. There's some of these new schemes that people are coming up with do not require blue or green lasers. They maybe require larger wavelength lasers, but still we need compact form factors with power. And to address that, maybe you guys are aware, DARPA just announced a new program to address these two particular aspects. How do you mass produce Rydberg sensors or Rydberg vapor cells, and how do you basically solve the compact laser problem? So hopefully, in a couple of years when DARPA's program's over, these two problems will be solved. Here's one of our attempts of making a compact vapor cell. This is one of our other photo arrays that we have, camera arrays we have. Basically, this is a 10 by 10 array that we basically are bouncing light. It's basically a 2 millimeter thick cell. We're bouncing light throughout the cell. We're using some green light here for cesium, and we're able to detect EIT in one of these compact cells on a very repeatable manner. Sort of a final thing that I haven't really talked about, and that is, I'll talk a little bit about it, but it's dynamic range. This is a plot. This is basically, I'll call it a Floquet plot. This is what we're showing here is and this axis here is increasing electric field. This axis here is probe transition. So what you're looking at the atomic states of a particular system that we set up here as I'm increasing electric field. And what this is really purpose of doing is demonstrating some of the elaborate structure you get in these atomic systems when you start applying fields. But with this, it tells us that we can now measure fields commonly in the lab pretty easily from about 3 microvolts per meter up to kilovolts per meter. And this little inflection point right here is corresponding to a field. I think it was 8 kilovolts per meter in the lab that we're able to generate. So it tells us one sensors can cover this huge dynamic range and potentially over a large frequency range. So with that, just to summarize here, I've sort of talked about this sort of fundamentally new approach of how one would measure and receive time-varying signals. As we said, it's extremely broadband. One compact vapor cell can cover a huge frequency range. It's an SI traceable measurement. It provides an independent method of how we're doing measurements now. It's compact. It allows us to measure very weak, very strong fields. And we said we can use that to do power. But it's really these unforeseen, unique applications that has got a lot of attention here. And I always like to leave a talk with trying to give a quote from a Nobel laureate. And my quote is from Bob Dylan, who says, "There's no success like failure, and failure is no success at all." I state this because, like I said, this is a project we started in about 2000, started thinking about 2006, 2008, and it took us several years to get traction. But like anything, with a good idea and enough time, it can be successful if it's a good idea. And it took a while, but it depends on how you measure success. I do it by doing cool science, but some people think about money. But the idea is just be persistent here, and good ideas do pan out. Once again, acknowledgments. I want I think several people who've helped us over the years. And then with that, I'd be happy to try to answer questions if you like. This is our group here in Boulder. And so with that, maybe I should turn it back over to you and answer some questions if there's time.
Well, Chris, thank you very much. That was remarkable how well you nailed the time. So we're losing a couple participants because it's the top of the hour here. I want to open it up to the chat to see if anybody has got a last minute question that they can sneak in here. But while you're typing, one of the things that I wanted to understand is the Quantum for National Security group. We've got a lot of people that are coming into the quantum space for the first time. So if you were trying to enter the Rydberg space now, and you wanted to identify the place that was going to be the most impactful for national security, where would you focus your efforts now? I know you've got a lot of history, and it seems like you've had your hand in just about every one of these application spaces at one time or another. If you had to pick one, where would you focus?
That's a good question. Like I said, you're not going to replace this, right? That's not where you want to spend your time. I think there's two regions where this is going to be, there could be some really interesting applications. One is in the, 300 gigahertz and above. There's some very interesting potential applications up there. But the other sort of interesting space is the low frequency side. And I know there's a lot of people who are really trying to understand what benefit you might get from low frequencies here. Once again, years and years and years ago, DARPA had a program called electrically small antennas. It was based on some metamaterial antennas and so forth. And the idea is, how do you make electrically small antenna? And in particular, electrically small, especially for low frequency. So I think, sort of the really low frequency and the really high frequency side is probably an application space worth spending some time in. Obviously from NIST, it's calibration. So we want the whole frequency range. But as I said, most people don't care about that. But it's really I think the really high frequency and the really low frequency side has some interesting application spaces.
Right. Well, thank you very much.